Swati Verma, Assistant Professor, Chhattisgarh Swami Vivekanand Technical University, CSVT Bhilai, and also subject matter expert of the course on industrial automation and drive. Welcome you all. Today we will begin with our ninth lecture focusing on the fundamentals of PLC programmable logic controllers. So let's start with the introduction of programmable logic controllers with its origin and evolution. The programmable logic controllers PLC are first appeared in the year 1960 with a form drastically different from today's available PLCs. The programmable logic controllers are initially built with logical components that replace the operation of auxiliary relays. These early programmable logical controllers were significantly more reliable than the classical electromechanical relays and require much less space in automation system. Over time, the PLCs evolved through multiple stages incorporating the digital components for timing, synchronization and counting, and they mainly eventually the adopting microprocessors which had already become the integral part of the personal computers commonly known as PCs. The modern programmable logic controllers now range from simple to complex systems of various sizes equipped with numerous extensions and interfaces to meet the diverse factory level needs, which includes the communication with other devices and computers. Additionally, there are multiple programming languages which are available to suit different user skills and are used to program today's modern programmable logic controllers. Every programmable logic control, regardless of its type and regardless of its size, can be described as a digital device featuring a microcontroller and a programmable memory that can store and execute the user instructions. These user instructions mainly involve the Boolean logic, sequential logic, timing operation, counting operation, and also the mathematical processing which allows the PLC to control the complex machines or overall industrial processes through digital as well as analog inputs and outputs. The fundamental structure of a programmable logic controller mirrors that of a personal computer, with having a key difference in the hardware available for input outputs and the operational manner of the microcontroller. While PCs focus on user interaction for various tasks and application, while the programmable logic controllers primarily communicate with the industrial environments and interact mainly with the input devices such as sensors, switches and buttons, and also with the output devices like the power relays, valve coils and the lights. The hardware of a programmable logic controller includes the essential components such as the CPU, input-output modules, random access memory, RAM, and a power supply. The programming devices used only during the programming stage can be either dedicated digital devices or a personal computer equipped with the specialized software. These programming devices mainly facilitate the conversion of a traditional hard wiring system into the flexible software solutions and embeds the necessary industrial automation components like the auxiliary relays and timers within the PLC itself. As you all see in the diagram, the conventional automation in comparison to the programmable automation, you can clearly see the difference and the various parameters of the conventional automation as compared to the programmable automation. Consequently, the implementation of an industrial automation system does not require the additional auxiliary devices and traditional automation circuit designs which are often replaced by directly PLC or programmable logic controller programming. The programmable logic controllers PLCs mainly operate cyclically in a process known as the scanning code. This scanning code mainly incorporates and involves continuous sampling inputs, executing the program, updating the outputs and repeating the same cycle. This scanning mode has a scanning time which indicates the operational speed of the PLC operation, and it can vary based on the microprocessor speed and also on its program size. This cycle operation enables the PLC or PLCs to detect and to respond to changes in the input states if efficiently, though the variations may occur faster than the scanning time and it can go undetected. So for the proper operations, the variation should not be more or should not be faster than the prescribed scanning time. If it is faster than the scanning time, then it will go undetected. For the PLC programming languages, they are not universally standardized. Typically, it includes the ladder diagrams, the instruction list, and a functional block diagram. With the ladder diagram being the most popular type of programmable PLC programming language due to their similarity to the traditional automation circuits which are now available. The IEC 61131-3 standard, which is mainly adopted in year 1993, it defines the basic PLC programming languages but also incorporate the variation and the incompatibilities persist among the different manufacturers available in the market. The PLC manufacturing companies mainly uses two basic type of constructions. First is the compact and second is the modular. In the figure you can clearly see the block diagram of the compact PLC manufacturing and second of the actual view which can be the modular view. Next, the compact PLCs are mainly solid, non-expandable units with a fixed number of inputs and outputs and are generally suitable for the small range of automation applications. They mainly integrate the power supply, microprocessor, input outputs and the other essential components. While the other hand, the modular PLCs, the modular programmable logic controllers mainly consist of separate and interchangeable subunits which are mounted on a common base, and it allows the customization for a medium to large scale applications. So we can customize according to our application need, according to a system need, we can customize the modular PLCs in a medium or to a large scale application. So based on the various parameters, based on various input output conditions and the special purpose module, we can meet the specific need of the system. But it has to be ensured the PLC fully corresponds to the application requirement. So mainly we can select from various input output and special purpose modules. Next, the oversized PLCs. The oversized programmable logic controllers have a CPU, the central processing unit, that supports a large number of input outputs and can be expanded using the communication units and interconnection cables available between various bases, and it allows and it provides the scalability for a extensive automation task. Now let's talk about the programmable logic controllers input output components. The PLC input output components are very crucial for interfacing between the industrial automation systems, input output devices and to the microprocessor. So you can say it is a very crucial or the main interfacing link between the industrial automation system, input output devices and between the microprocessor. It mainly executes a control logic. These modules are essential after the microprocessor but can vary in form, but typically include a power source, electronic circuits for signal conversion and a terminal block for cable connections and a mounting mechanism for its safety and to stand it. The most standard and the commonly used input output modules are the following. First is the digital input modules, second the digital output modules, third the analog input modules and fourth is the analog output module. First let's give an explanation about the digital input module. The digital input modules receive discrete signals from input devices and mainly it converts them for processing while electrically isolating them before transferring them to the PLC memory. Next, this discrete signal, DLC signal, can be either AC or can be either DC voltage. The input module mainly converts this voltages to a 5 volt DC, which is compatible with the microprocessor and the other components. The high power levels from the industrial devices are isolated from the low power signals at the microprocessor through an electrical isolation unit, which is mainly for the safety purpose of our systems or the components of our industry. Next, these signals are then multiplexed and are then transferred serial to the microprocessor through many smaller PLCs or through mainly smaller programmable logic units, which may use the parallel transfer without multiplexing too. So these digital input modules provide the visual indicators for each input state, means they can use an LED or they can use neon lamps for their indication or output indication. The digital input signals have mainly two states, on and off. The on state indicates the nominal voltage, while the off state indicates the zero or the null voltage. The modules which are mainly available are in various nominal voltages like the 24 volt, 48 volt, 110 volt or 230 volt DC or AC, but the 24 volt DC is the most popularly used for its safety purpose. Next, each DC module is characterized by its operating voltage and the maximum number of inputs it can sample, which typically ranges from 4 to 32 inputs. This input devices such as limit switches, selector switches, buttons, rotary switches, relay contacts, photoelectric switches, proximity switches, keyboard contacts, converters and arithmetic switches can carry the commands or can pass the information from the system or operator to the programmable logic controllers. These digital input modules contain the electronic circuits for its signal processing. For the DC signal, mainly a resistor circuit converts the voltage level, but for the AC signals, an additional AC to DC converter, which is known as ADC, or a bridge rectifier is used for the conversion purpose. Generally, a smooth capacitor stabilizes the rectified voltage and the resistance reduces to 5 volt. Then a diode is used to set the minimum detectable voltage. Then in the next step, the resulting low level DC voltage is used to power an LED or the light emitting diode, which is integrated with the phototransistor, which creates a logic signal for the microprocessor for its activation. Next is the optical isolation, which ensures the decoupling between its input electronics and the microprocessor, and which protect it from the electric faults and the noise and ensures its safety. Next, you can see in the diagram also about all the modules. The modules with the large input counts mainly require the proper power supply considerations. Inputs can have separate power supplies, which allows is to customize for various input devices with various powers with different power sources to connect to a same module. Alternatively, inputs may share a common power source, which necessitate the grouping by common voltage nodes. Some programmable logic controllers group inputs into 2 or 4 or 8 input sets with separate power supplies, as you can clearly see in the next figure. Next, the digital output module. In PLC operations, the results of logical processing from the automation programs are mainly stored in the output image table and are then transferred to the output devices through the digital output module. This output module results initially are the low voltage logic signals and are converted into power signals, which are capable to energize the output devices or to power up the output devices for indication. Unlike the digital input modules, this digital output modules convert and isolate the input signal for the microprocessor, but the digital output modules reverse this process. Basically, this digital output modules demultiplex the signals and store them using a latch unit and maintain the state of output signal between the various scans to ensure the consistent operation. The digital output modules shares a similar electrical circuits with input modules but are designed to handle the high power levels and currents and require the special components which includes the power transistors, the triac circuits or the relay circuits. These components can generate electrical and magnetic noise. So manufacturers have to keep this in mind and uses this surge suppressors and the varistors and fuses to protect the whole circuitry. These output devices are controlled by digital output modules and it includes the power relays, solenoids, indicator lights, alarm devices and electronic devices which often needs an on-off state change or a toggle change. The external power sources are necessary for digital output modules to supply a power to the output devices. Depending upon the module type, the input module type or the output module type, the switching elements like the power transistor, the triac circuit or the relays can be used, each having its specific characteristic or operation. Relays offers the good isolation and can handle both AC and DC voltage but can have mechanical wear and a limited time life. While the power transistors are suitable for DC voltage and provide the high switching frequency without any mechanical wear but are sensitive to current spike. So the power transistors have a large lifespan since it has no mechanical wear but it has a limitation that it is very sensitive to the current spikes. Next, the triac handles the AC voltage and are mainly durable, but it is also sensitive to the over voltage spikes and it requires the special safety devices or the fuses for its protection to prevent it from the over voltage and for the current spikes too. The digital output modules can have either separate or can have common power supplies which is similar to the digital input modules. The separate power supplies allows connecting the different or the various devices with having different power sources to the same module, while the common power supplies require all connected devices to share the common source. The configuration of this digital output modules depends on the specific requirement and the design of the automation system. So based on the configuration and based on the need of the application, we can select the proper digital output module. Now the analog input output modules. Initially, the programmable logic controllers could only handle the discrete inputs and outputs, which limits them or its operation to control the on-off signal type devices only and with the specific digital parts of industrial processes. This restriction of handling only the discrete inputs and outputs excluded the PLC from the analog control schemes. However, with the advancements in electronics led to the development of specialized analog modules for the programmable logic controllers operation. This analog input or output modules allowed the PLCs to interact with the analog signals, greatly expanding their control capabilities and applications in industrial processes. The integration of analog modules marked a significant enhancement in PLC functionality and now can be used in the analog control schemes. So initially the lack of using or handling the discrete inputs and outputs only is not there and we can use the analog input and output in the PLC operations too. Now comes the analog input module. An analog input module in a programmable logic controller is designed to interface with the analog signals. First, it converts them into digital values that the PLC can process. The core component of this analog input module is the analog to digital converter, commonly known as the ADC or the AD converter. This AD converter performs a conversion of analog input signals to the corresponding digital values or the variables. These digital values are stored in the module's memory, which makes them accessible to the central processing or CPU of the programmable logic control based on the requirements of the execution program or based on the requirement of the operation. To manage the variety of analog signals from the different sensors or transducers, the analog input module includes a signal adapting block. Now, what is a signal adapting block? The signal adapting block is a simple electrical circuit that transforms the input analog signal into a compatible form for the analog to digital converter. Some analog input modules have DIP switches to select the type of analog input signal, and it also allows or gives the flexibility without needing the separate modules for each and every signal type. For modules with a small number of inputs, they are typically dedicated to a specific types of analog signals. These analog signals are supplied in an analog input module, are standard and are compatible with the corresponding output signals of the analog input devices, which are mainly used sensors or the transducers or the switches. In the table, you all can see the most common analog input devices and the standard analog signals that we can find in the analog input modules as shown. Here the common analog input devices are listed with their analog signal range. First is the temperature sensor having analog signal range of 4 to 20 milliampere. Next, the pressure sensors having analog signal range of 0 to 5 volt DC. Flow meters having an analog signal range of 0 to 10 volt DC. Next, the transducers of any kind or any type generally having a plus minus 10 volt DC analog signal range. Next, the electronic devices, the analog output generally having analog signal range of plus minus 50 millivolt DC or either can have plus minus 500 millivolt DC. Another significant operational difference between the analog input modules and the digital input modules is that the former or the analog input modules are equipped with a local memory for storing the digital values of the digital inputs. Next, the analog input signals such as which are generated from the temperature sensors or the pressure transducers are generally standard and are compatible with the module's input requirements. These analog input signals are often transmitted through the shielded cables and which prevents the electromagnetic interference and could corrupt the measurement or the operation. Each analog input module usually contains a single analog to digital converter which can be shared by all inputs so that we can minimize the cost of operation. An input selector or can be called as a multiplexer routes each analog signal to the analog to digital converter sequentially manner. These digital values obtained from the conversion or obtained from the output of the AD converter are stored in the module's local memory and can be often referred as a data register. The CPU or the central processing unit then retrieve these values via the digital data transfer bus for processing according to the programmable logic control program instructions. The module's design ensures that analog and digital components are electrically isolated to protect and to save the PLCs, microprocessor and other electronic sensitive parts from their potential damage which can be caused by the electric noise or the surge or the any fault. The microprocessor within the module manages the overall functionality and includes the operation of the multiplexer, analog to digital converter and the memory. The conversion time for each analog input is relatively short and it typically ranges around 10 to 50 microseconds. Therefore, a module with multiple input channels can complete a full operational cycle in a fraction of a milliseconds too. This quick conversion time is significantly less than the typical scanning time of most available programmable logic controller applications, and it ensures the efficient and the timely data processing. Now comes The analog output module. An analog output module in PLC convert the numerical digital data from the programmable logic control central processing unit into analog voltage or to a current signal to control the analog devices. You can see the block diagram of operation of the analog output modules inside an analog output for converting a digital value signal to the analog. The digital values, typically 16-bit words, are processed by the programmable logic controller's program instructions and are mainly temporarily stored in the PLC's input and the output memory. These values are then transmitted to the analog output modules where they are converted into analog signals, which are commonly 4 to 20 milliampere current or ranges from minus 10 volt to plus 10 volt DC. This figure can illustrate this process and you can clearly see the process of the conversion. Now, although the digital word is 16 bits, only the 11 bits are used for representing the analog signal, while the remaining bits are used to convey the general information or for use for the timing signals. This strategy is similar to the digital representation of analog input signals, where specific bits can indicate the conditions like a measured value exceeding a range or the existence of a fault occurrence. The most significant bit typically indicates the sign positive or negative of the numerical value. Means the MSB of the digital word can indicate whether the word or numerical value is a positive word or a negative. Next, upon reaching the digital to analog converter, the digital word generates a corresponding constant electric voltage. This electric voltage means that the output voltage of the converter remains in the discrete form. For example, there are 1024 levels for a 10-bit digital word. As the digital input word varies, the output voltage changes in a piecewise constant manner and resembles real analog signals. To smooth this step voltage, an amplifier circuit is used to filter the output. The accuracy of this analog output depends on the frequency of the digital word update and is tied to the PLC or the programmable logic controller scan cycle. So to oversize the accuracy of the analog output, it mainly depend upon the frequency and on the scan cycle of the PLC. Next, the figure depicts the functional block diagram of the real analog output module, which is mainly similar to the input analog module. The digital and the analog circuits in the module are electrically isolated using an optical isolator. This optical isolator are used to mainly isolate and to ensure the safety of the system. The analog output modules often require an external power supply with specific voltage and the current requirements. The typical analog devices controlled by these modules include the small motors, servo valves, DC servo motors and drivers for high power motors with varying speeds. The analog output signals are always DC in nature, but they can also control the AC devices. For example, an AC motor controller like a soft starter can be driven by a varying DC signal from the analog output module. So, by applying a varying DC output voltage, for example a 0 to 10 volt range DC to the AC controller's input, the AC motor speed can be adjusted. The figure clearly shows the typical connection of analog output devices to a output module. Some modules offer a 4-wire connection as shown in the figure B for higher accuracy in the voltage application. This setup uses two additional wires seen as S plus or S minus which are connected directly to the load RL. This wires allows the module to measure the load voltage directly and can be applied in necessary or for the necessary corrections. The most common reason for discrepancies and changes between the desired and the actual output value is the voltage drop between the connecting wires and which occurs mainly due to the poor terminal contact. Now next comes the special purpose input and output modules. While most digital and analog input requirements for input output requirements for industrial applications are covered by standard modules, certain scenarios need special purpose input output modules. These special purpose input output modules handle specific signals that conventional PLC modules cannot process effectively and efficiently. Here are some examples of such applications. First, fast response input. In some industrial automation devices produce signals that change very fast manner that the scanning capabilities of a standard PLC or the standard programmable logic control cannot match. So the conventional input output modules cannot detect this fast or the rapid changes and cannot respond in timely manner, and the operation cannot be so effective. So in that application, also in that fast response input, we use the spatial input output modules. Next is the case of spatial motors. For the stepper motors and their driving circuits require the spatial pulse trains where the frequency affects the rotation speed and the number of pulses affect the angle of rotation. So to control these spatial motors, the standard input or output modules cannot provide these specialized signals. So here we use the specialized input output modules too. Third case is the complicated control problems. So the applications requiring the complex control such as analog PID control with specific response requirements cannot be managed or cannot be handled by the standard modules. So here also we use the specialized input output modules for a PLC operation. Next is the human machine interface HMIs and the data transmission. So here the transmission of data to human machine interface generally include the monitors, printers and the personal computers, which often requires a specialized equipment. Additionally, these specialized modules are necessary for PLC to PLC communication or for connection to industrial communication networks. For this and for similar cases, the spatial input output modules are designed. These modules typically features their own microprocessor which operates independently to perform the required task while it simultaneously connects to the main programmable logic control processing unit for exchange and for transfer of the data and the control signals. So that's all for this lecture. So in this lecture we mainly covered the fundamental of programmable logic controls, and under this we covered the digital input, digital output, analog input and the analog output module, and we also covered the need of the specialized input and output modules. So that's all for the today's lecture, and in the next lecture we will explore about the PLC fundamentals, where we will cover the PLC, the programmable logic control, central processing unit, the CPU and its power supply. So that's all for today. Thank you and have a nice day.